And we're back with more statistics online. And today the topic is the binomial distribution. And the binomial distribution is a name we give for a distribution of data that results from binary outcomes. All right. This example that I've mentioned in a previous episode is the blue M&M example. So Mars claims that their percentage of colors that they produce for the original M&Ms is as follows: with 24% blue. Now, if we were, imagine an exercise where we had a bunch of M&Ms and we picked each one up, and every time we found a blue one, we marked a cell in Excel, for instance, a spreadsheet, as a 1, and every time we found something that's not blue, one of the other 5 colors, we marked it as 0. What we'd end up with is a binary data set, and that data set would follow what's called the binomial distribution. Now, specifically with this lecture or this topic today, we're going to be interested in when we can approximate that binomial distribution, when we can approximate it as a normal. Because we already know what to do with normal distributions. We already know how to use the z-table, and we know the empirical rule that tells us that basically within 3 standard deviations of a normal distribution, we should have about all the data, around 100%. And so we can make use of that, and that's going to lead up into hypothesis testing and even into regression analyses. So we'll look at the binomial distribution, but with our eyes kind of focused on the normal approximation of the binomial distribution. Okay, so in forming this distribution, there are a number of conditions that need to be satisfied. Some notation first. We're going to be looking at the probability of x successes. X is a number of successes, and successes is just whatever we make it out to be. For instance, a blue M&M would be a success in our previous example, and one of the other 5 colors or any of the other 5 colors would be a failure. All right, success and failure in this case shouldn't have a positive and negative connotation. It's just whatever we're going to, it need not have that connotation. And in n trials, so n is going to be the number of trials, which could be picking up M&Ms. These trials are going to be satisfy conditions for what are called Bernoulli trials. The name isn't that important, but here are the conditions. There needs to be just 2 outcomes, hence binary, success and a failure. We get to denote which is which. These are n trials that are identical. Okay, so we're doing the same thing, or the same sampling technique is used. These trials are independent of each other, so we don't have any crossovers or spillovers in terms of probabilities. And 4 is very much linked to 3. The probability of success, which we are denoting with the Greek letter pi, does not change per trial, so it's fixed. And the probability of failure, which we could denote as 1 minus pi, or we have we also can denote that as q, is also fixed. Okay, and so the trials, 3 is that the trials aren't going to rely on each other in any way, and 4 is that the probability of success remains constant. Tossing a coin is a good example to keep in mind, right? Do I have a coin? I do, right? It's not an American coin, it's a euro, it's a 2 euro coin. Nevertheless, there's a heads and there's a tails. I guess the 2 euro sign would be my heads, and my tails would be whatever this bird represents in the European Union. Nevertheless, I flip it, only one of 2 outcomes can occur. Here I get the heads. And so that's my success, for instance. I could say every time I get a heads, that's a success, and I could mark the number of successes I get. There are, let's say, example 10 times I'm flipping this thing, so 10 tosses of a coin. These are identical, so if I'm going to flip a coin, I'm going to do it in the same way each time to satisfy these Bernoulli conditions. They're independent of each other. It doesn't matter what I did in the first one. The second one is just to move forward. And the probability doesn't change, right? The likelihood of me getting a heads is 0.5, right? Half the time I should expect a heads. That need not the case be that I will get 5 heads here and 10 tosses of a coin, but that's what I would expect to get. In the next slide, we'll show the expected value. Of course, these coins have to be well balanced, and I imagine the European coins are as well. This slide is just sectioning out the new notation, pi and q. I'll move forward quickly there. descriptive measures of the binomial distribution. So the descriptive measures of any distribution, right, at least for our purposes, is that we want to know what the shape is. Okay, we want to know what the mean is. That's our measure, our chosen measure of central tendency. It's not the only one, but it is the one we're concentrating on. And we want to know the measure of variability in the data, or sometimes we call this spread, variation. And our chosen metrics are the variance, and of course the square root of the variance, which is in standard deviations. And again, standard deviations is nice because it's in the units of the problem, whatever they may be. The first one, which I've already highlighted, is the mean. And for the binomial distribution, we will call this, the synonym for the mean here is the expected value. How many successes you expect to get, okay, is going to be our measure of central tendency. It's also the average. And so some of the new notation here is that capital E is expectation. The expected number X of successes is going to be our mean, right? Notice the Greek letter mu, and X is just here to as a subscript to indicate that we're talking about the number of successes. Often we drop that subscript. It's a very simple formula, just the number of trials times the probability of success. I already mentioned, when I'm flipping my coin 10 times, I expect to get 10 times 0.5, which is 5 heads or 5 tails. Okay, it's not impossible for me to get another number, but my expectation, and indeed the average number, is going to be 5. So let's look at an example here. I'm going to pause this so I can get ready to draw. Okay, we're back here, and we're considering a Stats 2 student that disappointingly chose not to attend class or study for the first exam. Not recommended. And there are 25 multiple choice questions, all right, and 5 answer options for each question. Okay, suppose that the student randomly guesses on each question, blindly just filling in the blanks with Scantron bubbles. How many questions should the student expect to get right? Expect to get correct? Well, if the student didn't study and knows nothing about stats, and indeed was just guessing, then the probability that that student guesses correctly is 1 over 5, or 20%, right, 0.2. So that's that population probability of getting an answer correct, the parameter value pi. Of course, there are 25 questions, and so n times pi, which is the expected value, is 0.2 times the 25, and so that student should expect to get 5 correct. Okay, so 5 out of 25. Of course, that's 20% in terms of grade, but the answer that we're looking for, re-highlighted in blue, is 5. Moving on to the second measure, okay, the second way we describe this binomial distribution is the standard deviation. This is the measure of variability. And remember, we have shape, center, and spread in no particular order here. And so the standard deviation of x, and x is the number of successes, is going to simply be the square root of n times pi times 1 minus pi, which can be rewritten as the square root of n times pi times q. All right? And so this is the formula. It's very simple to use. And the only thing that I want to mention is that given a sample size or a number of trials, n, okay, given the fixed number of trials, the standard deviation is going to be biggest when pi is 0.5. Okay, so pi is 0.5, 1 minus pi is 0.5. That gives us 0.5 times 0.5. The product here would be 0.25. That's the biggest number that this product can be. You can try that out, plug in 0.9 and 0.1 or 0.8 and 0.2, 0.7, 0.3. Doesn't matter. The standard deviation for a fixed number of trials is going to be largest when pi is right in the middle, 0.5. So that's where you get the most variability. Okay, so we have our measure of central tendency. We have the mean, the expected value. We have the standard deviation, which is our chosen measure of variation. And now what about the spread? Well, what about the shape? And lo and behold, the shape of this binomial distribution can be approximated normal, assumed it's normal, if and only if the following two conditions hold. N times pi, which is the expected number of successes, has to be 10 or more. And, it's not an or, it's and, n times the number of failures has to be, n times the probability of a failure has to be 10 or more. If these two conditions are both satisfied, then we can safely approximate this thing as normal. Okay? I'll show you a little demonstration to kind of illustrate why this is the case. Now, if these conditions if this condition isn't held, and we're going to call this thing the two-part test because it has two parts, two conditions. If this two-part test is not satisfied, then we don't know what this distribution is going to be. In fact, it's going to be skewed in some direction. It's going to be abnormal, and we can highlight a little bit more about that. But we're going to really concentrate on when it's normal because that's when we can use our standardized normal table. I do want to note that some textbooks use 5 in place of 10 in the two-part test. Okay, so depending on which textbook you're using, n times pi and n times 1 minus pi or q may only need to satisfy a constraint of 5 on the right-hand side. And what this does, and maybe it's not obvious at first, but when you think about it, it should be, using 5 in place of 10 is less conservative because it reduces the number of required observations or required trials to approximate the binomial distribution as normal. So it's easier to pass this threshold with 5. So 10 is more conservative. 10 is the one that we're going to use in this course, which is this final highlighted box here. The normal approximation of the binomial distribution, let's look at a simple coin toss example. I'm going to pause it again. So to get you thinking about how to form this binomial distribution, how to start creating it, we'll do a coin toss example, and I'm actually going to only do 2 tosses of a coin. And this is just to show you how to set this up, and then we'll go to the web to look at an easier way to look at multiple coin tosses. So let's say for now that we had one trial. I'm just flipping the coin one time. All right, and if we're going to set up a probability distribution, which is what this binomial distribution is, on the horizontal axis we'd have x, which again is the number of successes, and we'll call this the number of tails. It's not important which one is a success or failure here. So the number of tails is a success, and if I'm flipping it one time, and it, of course up here is capital P is probability, this is probability of getting that number of tails. It's possible that I get 0 tails, and it's possible that I get 1 tail. That's it, right? And we know that the probability of either of those happening is 1/2, 0.5. Right, so just shade this in for a little. Jazz this up a bit, right? Keep it interesting. Now, that's the basics of a probability distribution, and you just keep, it would just, the number of possibilities increases with the number of flips, right? Same axis here. Probability of x. But if I flip the coin 2 times, here I'm flipping it 2 times, it's possible I get 0 tails. It's possible I get 1, and it's also possible I get 2. Okay? Now, the breakdown of this, give me a little room over here. With 2 tosses, it's possible I get both tails, the first tails, the next heads, the first heads, the next tails, or Zilcho tails. And so for the 0 case, there's 1 out of 4, and so that's 0.25. For the 1 case, it's 2 out of 4. So, and then of course it's symmetric. So, what you can see here is that this the shape of this probability distribution here is changing. It's changing as I increase the number of trials. And in fact, the first one is symmetric here. The second one is looking a little bit more towards the normal shape. And in fact, this thing will start to tend towards normal. And the conditions laid out in the two-part test, are exactly those conditions that need to be satisfied to say, okay, it's close enough to normal. All right. So let's now go to the web and see if we can see what this stuff is all about. All right, this is a little web simulation of the binomial distribution, and it's useful because, well, it's hard to draw out by hand a binomial distribution with more than 2 or 3 trials. So here we've got an image that is pretty close to the distribution we drew in the previous slide, where we have 2 trials or 2 flips of a coin, and pi, the probability of success, is 0.5. Now notice that in this web simulation, instead of pi, they use p, but again, we use pi, and we can use this simulation to look at what happens with 5 flips of a coin, 8, 10. And if you think about those conditions in the previous slide, that 2-part test where n times pi had to be 10 or more, and n times 1 minus pi have to be 10 or more, hopefully you can see that the minimum number of trials or coin flips that we would need to satisfy those conditions would be 20 here. That's because 20 times 0.5 is just 10, right? And so this distribution that you see here in the graph is approximately normal. Statisticians would say this is close enough to normal for us to approximate it as normal, and then go ahead and use the z distribution to find probabilities under this curve. And so if we flip the coin 100 times, you can see what happens. It becomes much more of a smoother, traditional, normal kind of bell-shaped curve. And if we go back now, I want to show you what happens with probabilities of success that aren't symmetric or that aren't 0.5. And so we're looking at, let's say, 5 trials, and let's look at a probability of success as 0.1. And you can see that, well, if we just multiply these two together, 0.1 times 5, we know we're not satisfying that 2-part test for normality. And the picture of this distribution, hopefully you can see it's right skewed, right? The tail is directed off from the right-hand side, so it's right skewed. And it would remain right skewed for a while. But if we did enough trials, if we took enough trials, let's do 100, even with a probability of success that is relatively low here, 0.1, we have a normal distribution. And so this is how that 2-part test plays its role. Let's look at a case. We'll go back to 5 trials on an extreme probability of 0.99. And this is going to be skewed left. All right. But if we take 120 trials, let's make it 1,000 trials. Kind of hard to see. Let's reduce this to 0.9. We can see that although it's it's centered around 900 in this case, which makes sense, right? We know that the expected value is pi times n, so it's over here on the right-hand side of the distribution. It is a smooth normal curve, and though it's easier to see when you've got a probability closer to 0.5, that's what's driving that result. Okay, so from that web simulation, I have a number of pairwise comparisons between pi and n. and whether they're normal or not. And you can see that this first one is non-normal. Pi is less than 0.5. It's going to be skewed right in that case. Um, it doesn't satisfy the conditions of n times pi being 10 or more. And the rest of these, well, the next four are indeed normal. We can approximate them as normal. That's what that little squiggle means. And this final one with the pi, a high probability of success of 0.9, but a number of trials of 12. This does not satisfy the normality approximation conditions, and it will be skewed left. Okay, so let's look at a, you could ignore this iClicker thing at the bottom. This problem here, the probability of choosing a blue M&M is 0.24. We get that from this is a relative frequency, right? 24% are blue, says Mars. So supposedly we randomly and blindly select 50 M&Ms from a large bag. Now we're going to do this, replace them. We're going to satisfy all the conditions required for the Bernoulli trials. What's the expected, first question, what's the expected number? What's the average or the mean of blue M&Ms that we're going to get? Hopefully, this is clear. This is going to be 50 times 0.24. Okay? So 50 times 0.24 is going to give us 12. So we'd expect 12 blue M&Ms. The next condition is the standard deviation. So what's the standard deviation of the same data set, right? 50 trials, probability of success is 0.24. Well, I got to plug it into this. I need the square root of 50 times 0.24 times 1 minus that, so that's 0.76. And if you do that, if you multiply those things out, you get 3.02. So D here. The answer is D. Oh, can I? Might as well go back. Yeah, there we go. All right. Final question here. The probability of choosing a blue M&M is 0.24 again, 50 trials. What's the probability of choosing less than 7 blue M&Ms? Okay. Well, we know that because we expect back here we expect 12 M&Ms. We satisfy those conditions of 10, right? So so we can safely approximate this thing as normal. So when answering this question, we can go to our typical z distribution, our normal distribution, okay, and try to calculate what the probability is of grabbing out of 50, less than 7 blue M&Ms. All right? We pause here and we'll start the video. To begin, I will draw the normal curve. Number of blue M&Ms centered at 12. One standard deviation below the mean is 8.98. Two standard deviations below the mean, 5.96. The area we're interested in is the area less than 7, which is this area in red. And since we know that this distribution can be approximated as normal, we know that we can use the standard normal table, the z table. And this value is going to be 7 minus the mean over standard deviation.
which is negative 1.66. And if I look up negative 1.66 on the z-table, I'm going to get an area of 0.0485. So sloppy. 0.485. No better. Anyway, so the probability is about 0.05 or 5% of the time. We'd expect 7 or less blue M&Ms from 50 trials.